Okay, the number of real zeros. A polynomial function can have no real zeros than its degree. The degree of the polynomial tells you the maximum number of zeros. And by the way, that actually should make sense, because if I had, this guy has 3 zeros, all of multiplicity 1, I would have x minus x1 times x minus x2 times x minus x3. If I said this was degree 3, it can have no more than 3 unique ones. The minute this guy goes to multiplicities, then the degree jumps. So if they're all multiplicity 1, the most it can have is its degree, because x times x times x would give you a cubic. So in that sense, that's what it's saying. Now, this is what I want you to X out in your book, because then it says use Descartes' rule of signs to determine how many positive and how many negative zeros each polynomial function may have. Do not attempt to find the zeros. That's what we're going to be doing next. But we're not going to do Descartes' rule of signs. We don't need Descartes' rule of signs. We have our calculators. Descartes' rule of signs is really unnecessary. It's nice if you didn't have calculators. Now that we have the graphers, and it's just not the calculator, it's the graphing calculator, where we can actually see these suckers. Now that we have graphers, we don't need the Descartes' rule of signs, nor do we need the upper and lower bound rule. So essentially, all of that goes out the window, and the only thing we're interested in is how many of these things we're looking for. So that means what I need to do with this polynomial, how many do I have? Here's the power function. Which is the term of highest degree. And this says that the number of zeros, or the max number of zeros, is 5. I could have 5 or fewer. Y equals x to the 5th, which is a 5th degree polynomial, has 5, but they're all the same. It's 0, which is multiplicity 5. Now here's the next big theorem. We had a big one yesterday. Here is the big one today. And this is always so interesting because it's in mathematics. Well, it is a math class. I guess it should be a mathematics, shouldn't it? A rational zeros theorem. Let f be a polynomial function of degree 1 or higher of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the x minus 1 plus dot 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 plus a sub 1 x plus a sub 0, where a sub n is not 0. So if a sub n is 0, what it does is it reduces the degree of the polynomial because the first term goes away. So that says the leading coefficient isn't 0. And the constant isn't 0. Because otherwise it doesn't make any sense. Where each coefficient is an integer, if p divided by q in lowest terms is a rational zero of f, then p must be a factor of a0 and q must be a factor of an. And p is a factor of a0, q must be a factor of an. Now, here's my problem. I can't memorize this stuff, because suddenly I use p's and q's for different things in intermediate algebra. Before it's all over with, I'll confuse intermediate with college algebra, and then I'm really confused, and then you get confused because you're confused to begin with. You just get more confused. So I have to take this and write it in a form which is usable that I can remember.